All right, so good morning. Let's get started. How many of you enjoyed the assignment this week? If you had fun working on it, can you raise your hand? Nobody enjoyed it. So if you didn't enjoy it, can you raise your hand? So no one on two sides, only one person. All right. So if for those of you who, if you enjoyed it, can you tell me what you didn't like? And if you enjoyed it, can you tell me what you liked? Okay. No feedback. Logistic regression. So last time we talked about support vector machine, and our statement on SVM is that it's a very sophisticated classifier. So we can use it to construct decision boundaries between categories. And once you have multiple categories and you're looking for a classifier, you should strongly consider SVM. But SVM is not the only classifier. In fact, we know that you could also use the nearest neighbors algorithm as a classification algorithm. So we could determine what category something belongs to based on who their neighbors are. We identified a rule of thumb for determining the amount of neighbors we should consider, which is the square root of the total amount of data you have in your data set. And then we use the Euclidean distance as our distance metric to calculate, to determine who exactly is in our neighborhood, or who our neighbors are. So now we've examined nearest neighbors, we've done support vector machines, we've looked at the surface theoretically of the work, and you've also seen the three-dimensional decision boundary in the code that I gave to you. And you've used that to work on data sets that you generated by yourself. Hopefully it's some data that you're interested in, and you've kind of seen how this works in a way. I also had in my code a neural network model that also kind of is trained on the same data set and tries to learn the nonlinear decision boundary as well. And you can kind of see how the SVM performs with respect to the neural net model. Makes sense that the neural net model learns performs differently sometimes, because we know that, when you're trying to have these dichotomies, you don't always draw the same line. It's not always the same line that, in fact, separates the categories correctly. You could have a model that separates the categories correctly, but it might be closer to one than the other one, right? So the SVM model guarantees that you have the model that maximizes the margin. In fact, the so-called optimization problem that we try to solve mathematically, the first thing we do is we find an expression for the margin, and then we try to maximize the margin. And every maximum problem can be converted to a minimum problem, so we just reverse it. And then you could use any numerical package to solve this problem in a useful way. All right, so we're going to continue by looking at another model called logistic regression, but this model, we're going to treat it like 2 for 1. So logistic regression is essentially using everything we know about linear regression, but for classification. Linear regression so we talk about two classes of problems that we have in machine learning. We say that we have regression problems. This is problems where you're trying to estimate a number. And classification problems, these are problems where you're trying to assign a label or a category to something. So of course, it is really weird that we're using something called regression for classification. Well, when you try to use ideas that are natural to linear regression for classification, we call it logistic regression. Logistic in the sense that there is the logistic function, which is a function that looks like an S, and a saturate, you can think about it as it saturates at 1, and at the other, and the tail of the S is 0. So when it's at the bottom, it is 0, and when it saturates on top, it's 1. And so in this way, you can use it to classify things. When it's close to the saturation point on top, you would say, well, it belongs to class 1. And when it's close to the bottom, or you can say, you would say it is 0. So there is some form of threshold function, and once you cross the threshold, it's 1, otherwise it's 0. So it's kind of a binary classifier, right? The way we would treat logistic regression is very similar to the way we treat linear regression. We calculate the coefficients in the exact same way. We just deal with it after the fact in a very different way. You can kind of think about it as some kind of transfer function that allows you to either go to 1 or go to 0 in some sense. Okay, so let's continue by. So we've kind of already discussed this example. So let's look at linear regression. Can anyone tell me precisely what we're looking at here? What is this? Okay, no one. So I would show you what we're looking at, and in fact, we're going to do this in class today. So we would spend most of the time today on this slide, right? To kind of really, because what I've observed from my point of view is that as you continue into the future, even going to graduate school, you're going to build a lot of linear regression model. You have to have a very good understanding of it. What is it? What does it do? What are we really talking about? What I have seen from experience is that people talk about this linear regression model, but they talk about it like it's some really deep, sophisticated model, something doing magic, but it really isn't. It's just the equation of a line. And if you look at this picture, there is your data point, which is the blue dots, right? It's a two-dimensional data point. It has X and Y component, X, Y value, and you're plotting Y against X as usual. And that's the blue dot. And then you put a line in between it. This line has a slope and it has an intercept. And this is your model. The model in this picture is the red line. And every time you build a linear regression model, it is essentially you have described a line. You have described a line that I can put through your data points. And depending on the data points, a line might be good or a line might be really, really bad. For example, in this example, a line is quite decent because the data set itself has a good amount of linear relationship. You can see that the data points kind of cluster along the line, which means that even though the data set is not completely linear, but a linear model would give us a rough estimate. So this is essentially what we are saying when we build linear regression model, is that we're looking for a rough estimate, a rough predictor of the future, some kind of trend line, right? It's a rough predictor of what may happen. We know that the behavior is nonlinear. This data set clearly is nonlinear. And if I would be better off fitting a curve on this data set. But also, if I was supposed to have a linear model, it will not be the worst thing in the world. It will still be a decent model, a decent predictor for this process, or the process that is described by this data set. So whenever you build a linear regression model, you're essentially describing a line that you can put through your data set, a linear fit of your data in that sense. So that's what you're doing. So having said this, what do we expect should be, what do we expect a linear regression model to look like? Anyone wants to give me the equation for linear regression? Precisely from looking at this picture and understanding that, well, when we're doing linear regression, we're essentially fitting a line through our data points. It's going to be some line that we think is good. So some lines would be, for example, if you look at this red line, if I move it up to 10, and instead of crossing the y-axis at intercepting the y-axis at 5, if it intercepts the y-axis at 10, it will no longer be a good line for this data set because it's too high. So when you're doing linear regression, you're really describing a line. That's all. The job is to describe a line that can go through your data set. Anytime you hear linear regression, you think about line that goes through my data point, period. That's what you're doing. It's not any complicated than that. So the equation for linear regression is simply the equation for a line. And so can someone tell me precisely then what should our equation look like for linear regression? Atran, please.
It should be a straight line that the closest to all the point, or having the smallest distance to all the points.
All right. Sorry.
Can you hear me?
I can hear you. I heard what you said. You are absolutely correct. Can you say it again?
It looked like a straight line with the
Yes, it's a straight
smallest
line, but what's the equation of that line?
y equal w x.
Let me write that down. Hang on 1 second.
Y equal ax plus b.
I'm sorry, well, my tablet is not working. I'm trying to fix it. I don't know what happened. Okay. Sorry. Now it's working again. All right. So you said y equals to ax, right? Plus b. This is what you said?
Yes.
Okay, good. And this is what we also said last time. And I can write it in a number of different ways, and it wouldn't make a difference. I would just be changing symbols, right? I could write this, for instance. I could say y equals to alpha x plus beta. Does this change the meaning of what you said before, Atran?
No.
It doesn't change the meaning. I replaced A with alpha, and I replaced B with beta. Okay, so in the equation of the line, we know what is A. What does it mean geometrically?
The coefficient,
It's the coefficient, but what does it mean
the
geometrically?
the slope of the line.
The slope, right? It is equal to the slope. And the B is the intercept, right? B is the intercept, A is the slope. And when you have a linear regression model and they tell you, well, it is lambda x plus beta, and the point of this is that this generalizes to n dimensions, and I would explain what I mean by that. So one thing we've learned in this class is that y could be a scalar, meaning a number, right? Just a number. And if y is a number, we expect that x is a number. And we expect that alpha will be a number. And in that sense, we expect that beta will be a number. But what if y is a point on the plane? What if y is a vector? Well, we expect then that x is a vector. What then happens to alpha based on what we did last time? What is alpha? If x is a vector, what is alpha? That when?
I think Alpha is a vector.
Alpha will be a vector. And so what kind of multiplication is this? This has a name. We did it last time. Anyone wants to remind us? Atran?
It's dot product.
Dot product. Dot product. And we know that for the dot product, alpha is going to be the transpose of the dimension of X, right? Of the dimension of X. So if X is n by 1, alpha would be 1 by n. And the dot product as such will be 1 by n multiplied by n by 1. And this is going to give us what? What would this produce? Atran?
It is 1 by 1.
It will give, well, what is 1 by 1?
What?
What is 1 by 1? It's 1 by 1, but what is 1 by 1?
A vector.
1 by 1 is not
number.
a vector, a number. 1 by 1 is a number. It gives us a number because it's 1 by 1. Okay, Atran, thank you so much for answering a lot of questions. I will give you 5 points.
Thank you.
Okay, so from last time, I would thank you, Atran, for helping us kind of remember what we talked about. We learned that if you multiply two vectors together, you do a dot product. And usually what you do is you would transpose one vector so that you can have a vector multiplication, because we know that it is impossible for you to multiply n by 1, n by 1, multiplied by n by 1. This is not going to work because these dimensions doesn't match. You guys already you've learned the rules of vector algebra. Vector algebra says that for us to be able to multiply two vectors together, then this has to match. So the way to do that is by transposing this. So we have to go to alpha transpose, and then we will get 1 by n, and then we can now multiply with n by 1, because now these two will match, and this will give us 1 by 1, which is essentially a number. So we learned that last time, this idea of the dot product. And so we know that on a line, or let's put it this way. So the equation of a line, okay, equation of a line is y equals to alpha x plus beta, when y is 1D. Consequently, x is 1D, alpha is 1D. By 1D, I mean one dimension, which means a number. Beta is 1D. But you can generalize this to n dimension. So when you take this equation and you generalize to n dimension, it looks the same way, but now it is in bold. It is written in bold. Y in bold, which tells you it's a vector, is alpha in bold, which tells you it's a vector, x in bold, which tells you it's a vector, plus beta, which is not in bold because this is still a number. Well, actually, in this case, this is in bold because it would be a vector as well. But in this case, this is a vector. This would be a matrix or a vector space, right? To be completely clear, this would be an right? N by M, and this would be the alpha would be N by 1, and of Y would be M by 1, and beta would be M by 1. Okay, so let's go back and talk about that some more, just dimensions still. So in high dimension, our Y, in fact, I will do it this way, is a vector. Okay, this is sign for a vector. So we have M of them, it's M by 1. So what that means is that our alpha would be N by 1. What does this mean? It means the length of my data set, the amount of features in my data set. So I have N features in my data set, but I have M of them. M is the total amount, N features. M is the total amount of data. So every data has N features or N columns, if you will. So for example, in our, let's go to source code and look at what we're talking about here. So look at our data set, this classification nonlinear.csv. We have three features and one label, right? So height, weight, GPA, but we have a lot of it, right? We have a lot of it. So the total amount of data, the length of the array containing my data set will be M. The amount of features that I'm going to be using will be 3, right? Will be height, weight, and GPA. Those are the features. That's N. Total amount of data is M. The amount of features is N. So N in this case is 3, and the length of my data set F would be, in fact, I would, this is a bit premature, but let's do it. We're waiting for the code to run and for that breakpoint to be executed. It's usually a bit slow when you run the first time, and there we go. So let's look at this with watch. So the length of my data set, the number of data points that I have is 100, but the amount of features that I have in every single data point is 3. All right, looks like something happened to my Wi-Fi there. All right, so I was saying that the total amount of, you can still hear me, right?
Yes, we can.
Okay. So I was saying the total amount of data that we have in our data set is 100. That's our M. But every data point has 3 features, right? So if you look at every single Let's go here. All right, so it's easier to see this way. I have 100 of this, 0 to 99, and each one of them has 3 features, right? 172, 152, 3, and then there is a label, right? But I have completely only taken the features. In this case, I dropped the label, so it's even clearer here. So I have 3 features and 100 data points. So that's what we're talking about here. Okay, so we're talking about n by 1. N is the total amount of data, which is our number of data points that we have. N is the number of features that we have. So we have alpha at this point, and we have alpha x. So our data set that we just saw is going to be what? It's going to be so depending on how you want to do this, I will write it's going to be n by m. So, or you could also say n by n if you want to write it that way, but I don't, it's confusing, so I will write it in the reverse. In a way that so we write it as n by m. Why am I doing it this way? Because the vector algebra is easier for us to see this way. We simply transpose alpha, and then we know that we're going to end up with n by 1 or 1 by m, and we can transpose that and we'll get n by 1. So it doesn't really matter. So and in fact, we can continue by simply writing beta here, and this also would be n by 1. So we expect that whatever we get here would give us n by 1. So you can continue by saying alpha transpose x. So this which will result in 1 by m, and you can transpose the whole thing back, transpose this, you get 1 by n by 1, and then you can add it to your beta, and then you would end up with n by 1 matrix, which is your y. Right? So that's that. Or in fact, if you want to be more precise about this, you could write this then as y equals to x alpha, or you could write this as x beta. Whatever symbol you want to use, it doesn't really matter. You're saying the same thing. And when you do that, then it's easier. You can do n by n, and your coefficients would be n by 1. No need to transpose. This would give you, this matches, this straight away give you n by 1. And I'm showing you this because in many textbooks, you would see this. You would see this formula on top. This is how it's written. It doesn't matter. It's still the equation of a line. In fact, when you go back to our slide, it is kind of written in this way. It's still the equation of a line, but just that when you write it this way, the algebra is obvious, right? M is n by 1. N is n by n. Beta, which is the coefficients for each of the coefficients, would be n by 1, and you end up with n by 1 when you do the vector algebra. So here's a question, continuing with this, because this is something that will repeat itself. So we're still here, n by 1. So now we have x, which is m by n. Beta, oh, let me write this. X, which is n by n. And beta, okay, which is the symbol for a new coefficient, which is also n by 1. So can someone tell me why beta is n by 1? Why is beta n by 1? What is the reason? Why is beta n by 1? No one? Dong, please.
I think the reason is if we want to resolve with the matrix n by 1, so
No, I
we need
don't. That's correct, but this is just a vector algebra reason. Why? I mean, why is the practical reason? Why is beta n by 1 in practical reason?
because n represents the number of features. So we are finding the coefficients. We are finding the coefficients for
So
each feature.
I would give you 10 points for this. You might be surprised by why I am giving you so many points, but this is a critical understanding that you just demonstrated. I want to make sure I have your full name. So this is equivalent to one homework. You just for free by demonstrating this understanding. It shows you've been working on your free time. Because the features, we have n features, and this beta contains coefficients for the features, our attributes. This is the masterful performance by Dong. He understands that this data set is a data set, it's a collection of data points that have n features. These features are attributes, and these attributes, they need coefficients. You have to multiply those data with coefficients. So if you have 3 attributes, you're going to have a vector that has 3 coefficients. If your data set has 4 attributes, you're going to have a coefficients vector that has 4 coefficients. If your data set has 5 attributes, you're going to have a vector of coefficients that is 5 by 1. If your data point has 7 attributes, 7 features, you're going to have a vector of coefficients that has 7 coefficients. Every feature has its own coefficient. Weight has its own coefficient. Height has its own coefficient. GPA has its own coefficient. Every feature, every attribute in your data has its own coefficients. Beta is a vector of coefficients. That's why it is n by 1, because beta is a vector of coefficients, because every attribute, every feature has its own coefficients. That's it. So, and now someone tell me, what is now machine learning in this sense? So we're still here. Y is m by 1. Our X, which is our data set, is m by n, right? We know that m is the total amount of data that we have. And n is the number of features. And there is a magic there, okay? From my data, I get a result. I am saying that from my data, I get a result because I multiplied with a transformation. And that transformation is a vector of coefficients here, which is n by 1. What then is machine learning? Anyone wants to explain it for me? What is machine learning in this case? Once you have a formula like this, what is machine learning? What are you trying to do when you're training? Dong, I think you can do this. I think you know the answer to this. When you're training, what then are you trying to do? What are you trying to achieve? Okay, man wants to go for it. Go on, man.
Yeah, so in the term of machine learning, when you have a data set and you want to train the model,
that's not what I asked.
Up...
I'm saying that now that you know in this equation, the way it looks, y equals to x multiplied by beta. So this is an equation that your machine learning algorithm is trying to solve. What do you think machine learning means in this context? Long, please.
I think it's trying to find the coefficient of every feature.
It's trying to find the coefficients. So now we know what we're doing. What does the machine learning model do in this situation? It tries to find the right coefficients such that when you do the vector algebra, you get the y back. So what am I trying to learn? What am I trying to learn? I'm trying to learn the correct values of beta. This is machine learning in this case. Machine learning is just learning the correct values of beta. I know what my model is doing. I know my model takes an x, which is n by n, returns y, which is my predictions. What then is my machine learning? What is my model doing? My model is simply trying to learn the correct values of data. So when I feed it this data, it tries to learn the correct values of beta. So Long, I'm going to give you points for that. So 2 points, right? I'm trying to learn the correct values of data. It's important that you know what you're really doing, because nowadays the code is very simple and all of you can do it. But what are you really doing? When someone asks you, what are you doing? You should know what you're doing. You're trying to calculate from the data the correct values of beta. You know that your prediction is an n by 1 vector. Your data set can be described as an m by n matrix, because m is the total amount of data set that of data you have in your data set, and n is number of features. When you do the vector algebra with a vector called beta, which is n by 1, you're going to get n by 1, which is your prediction. So your machine learning then is simply estimating the correct values of beta from the data. It doesn't matter what method you use. You can do this with a neural network, and you can do this with a linear regression model as well. Well, you're simply trying to learn the correct values of beta. That's the problem. So you have to be able to understand the problem, regardless of the tool you choose to solve the problem. At least you know you have a decent understanding of the problem. All right, good. So let's go back to our slide. And I told you that we're going to spend a lot of our time on that first slide, because a good amount of, you go to graduate school, you would keep talking about regression. It's important that you really know what it means. So we have a bunch of data set, and we have put a line through it. And this line, when you're on a two-dimensional plane, it's simply a line. Y is a number, X is a number, alpha is a number, or beta is a number. And you can see that, in fact, in our case, they've gone with the weight transpose already for us, and xi, or whatever it is that they've chosen. But when you look at other books, you would find that it's however they write it, whether they write weight transpose or they write the data set first, you know precisely what we're going for, right? The weight transpose is to tell you that you need to transpose in this case, in this simple condition, you need to transpose the vector of coefficients so that you can do the vector algebra, right? So that's what that is. But you can generalize this to any dimension, right? X could have many features. It doesn't have to be a point on a two-dimensional plane. It could be a point on a high-dimensional plane, right? We also said that a vector is a point on a plane. A vector is a point on a high-dimensional plane, right? A number is a point on a line. A vector is a point on a high-dimensional plane, right? And in fact, you can think about a number as like what Atran said. A number is simply a 1-by-1 vector. That's a number. That's a scalar, right? So in some sense, it's a point on a one-dimensional plane. So there is a way you can kind of think about generalizations of scalars and vectors, and you can kind of have a conception in your mind. And the English for that is a point on a plane, or a point on a plane or on a line. That will give you a scalar or a vector, but we're still talking about a point. So doesn't matter what the dimension of the plane is, this idea will still be relevant. You know, on a two-dimensional plane, you put a line through the points. The line, you can visualize it in this sense. On a 15-dimensional plane, the line will be very difficult for us to visualize, but the notion of a line going through your data point will still be kind of valid, even on a high-dimensional plane. This idea of linear regression extends to a high dimension, right? Because there will still be a line going through those points, those high-dimensional points, right? You have a 5x1 vector. It's a point on a 5-dimensional plane. We cannot visualize it, but you can put a line through it. A high-dimensional line can go through it as well. So this is the simplest form of this is on the 2-dimensional plane where you have points. These points have 2 dimensions, and the line, of course, is this. The equation of a line is quite simple as well, right? So, and you would find that a lot of the ideas that you can represent in 2 dimensions can also generalize to high dimension. When you're working on your data set that has many features, you can always think about the simplest form of it in 2 dimension, and whatever solution you have in 2 dimension, usually it could generalize to high dimension. It would work as well. Okay, so we know that in linear regression, our idea is to have a predictor for the future that follows this line. So when you ask me what if given a particular x, what is the next value of y, I would use the equation of the line to tell you what the next value of y would be, and it's going to be on this red line. It's not going to be perfect, but it will be an approximation of what it should be. Why? Because this data set has a lot of linear relationship. You would see that when the x is high, the y is also high. We don't know how high, but we know it would be somewhat high. And when we predict a point on this red line, it gives us an approximate value for our y. This is not a great model for this data set, but it's an approximate model. Every time you fit a line through your data set and your data set is nonlinear, what you're doing is you're generating an approximate model. This is the triumph of linear regression. It's these approximate models that you can build, and they would be able to give you an estimate, a decent estimate, right? And usually when you have the notion of a decent estimate, there is the idea of a standard error, right? Some kind of correction, if you will. So, but instead of thinking about it in that sense, I want you to think about this line that you're looking at, right? If I take a line, this line has 2 properties, right? One is the slope. In fact, this line has 1 property, simply the slope. But the system has 2, in the system, the line has 2 properties. It has a slope and then it has the intercept, but only if you're looking at the system. The line itself, just the line without considering the system, only has a slope, right? It has a slope. It has how inclined the line is, right? And in fact, how the slope of the line is simply in relation to the x-axis, if you will, right? So geometrically, the angle this makes with the x-axis would give you this slope, right? If you increase the angle, then the slope would also kind of the line would be more steep. The slope would go up. So the slope of the line technically has nothing to do with the y-axis, right? I mean, from the reference of the x-axis, right? So we're not looking at it from this side. We're looking at the angle that it makes with the x. And usually in real world, when you're looking at how steep something is, you're looking at it with the surface, right? Which in this case is the x-axis. The point of the y-axis here is simply to give us this intercept. But at that point, you're looking at the system, the plane and the line. So why am I saying this? Why all this talk? Well, it's to tell you that the most critical parameter that you want to calculate to describe the line is the slope. You have to tell me the slope. But if you tell me the slope, I can draw that line anywhere, right? In fact, I can draw that line and then it can go through 10, it could go through 15, the same line, but it will be a poor model. It will be a model that is correct in its trajectory, right? It would behave, but the scale will be too much. The numbers that this model will be given to me will be outside of the numbers of the data set. Is anyone following what I'm saying? So imagine that I have a line that goes through 10. This is still a correct model. This line up with the same slope that goes through 10, but this line is going to be predicting numbers that is outside of my numerical range. So that would be the error, if you will, the flaw in the model. And this line could go through 15, it could go through 5,000. It would behave the same way as this line. It would give me, for increasing values of X, it will give me increasing values of Y. If I generate predictions with my line that intersects the Y-axis at 5,000, the behavior would be the same. Increasing values of X will produce increasing values of Y, just that the values would be quite larger than what I expect. So the point of the intercept, the point of the B, in this case of the so-called bias, is to bring the model into our numerical distribution so that my prediction is drawing from the same range that my data is in, right? Because without the bias, this line could be anywhere. So I use that bias to kind of move my model up and down so that when I predict something, the numbers would be in the range in which my data is actually drawn from. So this is kind of the idea of this bias, which kind of moves things up and down. All right. So before we learn how to use this idea of linear regression, so-called equation of the line, to do classification, let's actually see if we can implement this in a very, very easily right now in class. So I have this Python script called linear regression. So let's begin by saying class linear regression. And then, of course, I want to maybe import NumPy preemptively. Why is that? Because I want to generate some random example. And if you remember, just to show you that we kind of already did this before when we did nearest neighbors, right? Where we use NumPy to generate our random data. So not to waste time, I would just copy that and find a function called run. And all right, so this should be working. Okay, so we would like to maybe visualize this this data set. So to do that, we need to import matplotlib, right? Matplotlib as plot. So that's that. So what we can do here is we can just visualize a scatter plot of this. So we can separate it like this. using this comprehension. So X in original. All right. So let's have the way of looking at what we have. So we have model is our linear regression. Run. So we should have self. So this could work. And then we can execute this script. All right, so let's look at what we have here. Okay. We can observe this. All right. So we want two features. And we want like 0. Y can change this to data point, so it's not readable. And we can simply add marker, color, and the color, make it red. Right. Read, we can set this to true, and then we can plot out show. All right. So let's run the scan. Let's see where we are. Okay, so we have a sequence of X's and Y's, and we hope to be able to plot them and see. Okay, let's see what this looks like. pie plot. Okay. So this is what we have. So clearly this is not a good, this is not this is not a good this is not if you will, this is not a great example for a linear model. Okay, so what we can do actually is so now that we have this, we can let's call C our coefficient, and let's call it 0.8, or maybe even let's call it I don't want it to be too large, but big enough, maybe 15. So what we would do is we would do so we would multiply every x by 15, and we would so we would do that, and what we would now do is for every other data point, we would also multiply. Okay, I will do something. For every other data point, we would multiply the y value that we generate. Okay, and we can simply change this to yi and y at I. Actually, let's change this to data point. change this to actually original data. All right. I will change this to a sample. Then I can. Okay. Let's see what this looks like now. So the idea is to get a fairly linear data set that we can work with. Let's convert this into an actual function. Bad. Okay, so some of it would depend continuously on X, others would not. Here we can use Y latest. All right. Okay, so this is better. So you can see this data point. I try to add some noise so that it does not just look like this straight line that already goes there. So the point of this is you can see that well on some level you have some data points where the Y only depends on X, just continuously depends on the X and nothing else. And in this other noisy one, it depends on the X, but it kind of varies a little bit. And in fact, this is what I should do for my entire data set, is I should just kind of mix it up like that. So yeah, let's get rid of doing it for some of it and let's do it for all of it, so that we can have this nice noisy data where you can kind of see that there is a lot of linear relationship because, of course, the original data Y depends solely on the X value, but now it's kind of noisy in that sense. We've kind of add some randomness, and you can kind of see that this is very close to the data that we have in the book. It also kind of has a very strong linear relationship. And the idea is higher values of X should produce higher values of Y. I mean, that idea is there. Okay. So instead of making this red, I would make it blue so that we can make our line blue. Right. So I Let's make this blue so that we get, so now we have this interesting data set that we can now feed a line through this. Okay, so there we go. So now we have this nice little data set. Our linear regression model should be able to feed a line in this data set. This is what we would like to do. And how do we do that? So the first thing I would like to do is to kind of show you intuitively how you would do this. So there's something called the centroid method. But before we actually write the code, let's talk about it. So I have my y. I have some coefficients. Let's beta. I will continue to use beta because I think it's more popular. And I have x. Okay, these are just numbers now. So if I know y and I know x, how would I calculate beta? Can someone tell me how I would do that? Yes.
Yes. Beta equal y by x.
Exactly. So this is it. Simple algebra. This is it. Simple algebra. So now what happens when I have a distribution? Okay. So imagine that y is a set such y of yi and x is a set of xi. Like we have. So how will I calculate then? How will I calculate beta? Question. How will I calculate beta? So this is going to lead us into a real understanding of what we're doing with linear regression and what it is. What are you really regressing? No one has an idea? Okay, good question. Jessica, please.
So if I remember correctly in the book, it will be the covariance of xy times
It's too complicated, so no. That's not a simple way of thinking about it. I want you to think about it from first principles. So the first question I would actually like to ask you is, okay, why regression? This term, regression. Why? Why did we? What is this? Is English? I mean, but why select this word? Well, what are we regressing? What does it mean intuitively when you see regression? How should you think about it? Okay. Can someone tell me what this means? A measure. Oh, Jess, you want to tell me why regression?
Yes. Regressions, I think, is like about the relationship, like when exchange, how much even change when exchange.
No.
Why we change.
Not really. Also not correct. It's what you said is true, Jess. What you said is true, but it has nothing to do with why we call it regression. To really understand why it's called regression, we have to first of all talk about measure of central tendency, and if anyone can explain this. So, Jess, do you want to try to explain measure of central tendency?
I'm not sure about it.
Okay, good. So anyone has an idea on measure of central tendency? Okay, I'll go on. So the idea is this. Imagine that I have a series of numbers, right? X1, X2, X3, all the way to X1b, all the way to make my point, X 1 trillion. Okay, this goes all the way to 1 trillion. All right. The question is, can I describe this without listing all the numbers? Can I describe this sequence? Okay, this sequence goes to 1 trillion. Can it be described without listing it? Can it be described without listing all of the contents? Anyone? Yes, Atran?
So I think the method central tendency is to a statistical value that represents it center or typical value.
You were almost correct. The measure of central tendency is a way of describing the sequence without listing it. So instead of telling you what the sequence is, I would simply tell you some statistics that describes it. For example, I can tell you the mean. I can tell you the average. Once I tell you the average, you have an idea of what the sequence is. If I tell you the average and I tell you the variance, so, or in fact, let's not use variance. I tell you the standard deviation, okay? Which means this is the measure, this is how, this measures how a random data point would depart from that average that I've given you. Then I have kind of almost completely described the data point in the sense that you can generate that data point without, all you need to generate the data point is these two values, the mean and the standard deviation, because the variance is just this, which is the other parameter you need, is just the square of this, right? Sigma squared. So to make my point, whatever this is, whatever number this distribution is, I can simply say it follows normal distribution. It's going to be centered at the mean. This is, you've already told me that. And that I know what the standard deviation is. I know that 68% of the data, 68% will be within one standard deviation. So this is mean plus 1 SD. This is mean minus 1 SD. And then with mean plus 2 SD, minus 2 SD, and then you're going to be left with 5% roughly here. Maybe 5%. So my point is, you know that 95% of the data is going to be within 2 standard deviation of the mean. So when I tell you the mean and the standard deviation, I've described the entire distribution, because you know that the bulk of the data, 68%, will be within 1 standard deviation of that mean. So when you give me the average value, you've told me a lot about that distribution. 68% of the data would be 1 standard deviation away from that value. So you don't have to list the value from 1 to 1 trillion. You just have to tell me the average. So when we talk about a measure of central tendency, we're saying that, can you tell us something? Can you describe this distribution in some sense, right? So the most common measurement of central tendency is the mean, right? Is the mean. But there are other things. There is also the mode. What is the most common occurrence? You can think about the median. All of these are measures of central tendency in some sense, but in a strictly rigorous sense, we always go with the mean or the average. This tells me a lot. This tells me quite a lot. It tells me the most occurring the most occurring number, and if this is categorical, then the mode is quite frankly very, very relevant. For example, imagine that this is a distribution of grades A, B, C, D, right? You telling me that A is the mode conveys a lot of meaning, because it means that this is the most occurring category. So so but when it comes to like continuous data, the mean or the average is the standard measure of central tendency that you want to go to. And why am I saying all of this? When we talk about regression, this is why I said what Jess said was true, but has something to do with why we regression. We are indeed regressing the mean. And then you can go back to my formula here. If we are regressing the mean, it means that I am comparing the mean of this distribution of X to the mean of this distribution of Y. This is really what I am doing in regression. So I am regressing the mean. This beta tells me that the measure of central tendency of this distribution of X, which is X bar, is related to the central tendency of this other distribution of Y with this coefficient called beta. That's it. This is how this works. So when we go to our pretty picture and we run our code, the line that we want to put through our data, right? So what happened? Okay. The line that we want to put through this data set, we calculate it not based on the individual data set themselves, because that's not what we're regressing. We are regressing the distribution of the Y, the measure of central tendency of the distribution of the Y, which is the average in this case, or the mean, and the measure of central tendency of the distribution of the X, which in this case would be the average as well. So those two quantities, those two averages, they are related by some coefficient called the slope. And that's what's going to determine the line, the slope of the line that I'm going to try to fit through this data. And this is the critical idea behind the centroid approach. So when I talk about the centroid approach to calculating the slope, we're trying to regress. You have to keep in mind that we're trying to regress the mean, right? So the critical first thing to remember is that we're indeed regressing the mean. My goodness, my keyboard doesn't work today. The mean. So it makes sense to first calculate the mean of X, the mean of Y, and using what that said and using simple algebra, determine the slope. Okay. So this is precisely what we're going to do here. This is takes X, comma, Y, and so we define our own function called not that we need it, but why not? And we have accumulator equals to 0, nums. And then we will, what's going on? Then we simply want to return All right. So why did I do this? There is no reason to do this, but I just wanted this to be obvious that we're doing a simple average. We sum the numbers together, we divide by the length of the numbers to find the average, which is the mean, and this just makes it more explicit. In fact, I should call it find mean. So, and so the first thing we do here is x bar is itself dot find mean, and this takes x and y bar or y mean, whatever that is. Okay. So this is the idea for a centroid. So and here, after just before we plot, we can in fact we can move these functions up. And we need so coefficients. The model coefficient. Will be self.centroid. We pass in our x and y latest. And what we'd like to do is now have our model, so our linear model. Then is simply model coefficient multiplied by x. So we can now plot or the line. I think we can do that. Let's just simply plot. Should do that. It's our linear model, which is our line that we are fitting, and all can be read. Okay, let's see if this works and how it looks. Let's use work. All right. Okay, so we can see that we've been able to use the centroid method to be able to essentially generate our model. And we've been able to kind of fit this data set with our model, which our model is this line, which is our linear regression model. And this is a pretty decent fit. If you agree that this is a good fit, can you raise your hand so I can see who is following what I'm doing so far? Okay, only 12 people agree. So which means the rest of you don't agree, and you have to tell me what the better fit is if you don't agree. All right, so put your hand down. So if you did not raise up your hand, if you didn't raise up your hand before, can you raise your hand now? So about 27 people should raise their hand. If you don't raise your hand, it means you're not paying attention. So if I don't see 27, it means you're not listening. And then you can tell me you don't understand, but you don't listen. So there is still 13 people that I expect to put their hand up. So okay, so man, I will put you in the spotlight. You didn't agree it was a good model, so you have to tell us what's a better model. All right. So man, can you go on and tell us what's a better model than this right now?
Yeah,
And-
sorry, I did actually put my hands in the first place.
Oh, okay.
Yeah, thank you.
You escaped. All right. If you didn't put your hand up, can you put your hand up again so I can pick someone else so you can have a chance to tell us what's in your mind? No one wants to do it now. Okay. So clearly, a lot of you're not paying attention, or I don't know what I can do there, because the point of showing you this is because I can show you this slide and move on. It's already in the slide, and I posted the slide. How many of you know that I could show you this slide and just forget about it? I mean, I can show you the slide. It's already there on slide. And I don't have to show you this other building this slide essentially is so you can understand what's going on from first principles, so you don't have to memorize it. You can Google this and you would see this picture, but if you don't understand the picture fundamentally, I mean, what's the point, right? So the point of spending a lot of time on the slide is so that you can understand what's really going on. You don't look at this data and then, because it all looks like wonder, right? Because you're not a data scientist, you don't do this every day. So when you see it, it looks like magic. But when I show you and we do it step by step, it stops looking like magic and now you understand what's going on. This is why I've spent this amount of time talking about everything we're doing. So we are in fact regressing the mean, which is why we compare the means of the two different distributions. And then from the mean, we calculate the coefficient, which is the slope of the line. And then we can use that to fit the data. And that's what I just did in my code. And as long as you see that this is a really good model, and it's as good of a model as the one we found in the book. So this is the model from the book, and this is our own model. They look very somewhat close. Definitely, this model could be somewhat improved, right? So if you essentially reduce the slope of this line, then this model will be slightly better, but this is already a good model, right? So by reducing the slope of this line, then this line will rotate a little bit here and but I don't necessarily know that that would even be better because there is a cluster of points here. So this might, in some sense, be a better model, but then you can argue that there is a cluster of points here. So a little bit of a rotation would improve this model. So a decrease, if you will, in the slope would help. So the centroid approach is not the greatest, but it does work. It does work, and this is what I was trying to prove, that you can use the centroid approach right away, straight away, and you would get a really nice you get a really nice model. So for your homework, you're going to implement the least squares approach. So there is something called the least squares method. And you would do that here. So essentially, the way the least square method works, it works closely based on what you have already learned from neural networks. And I would explain that so that you have some form of understanding. So there is so you start, so you have your equation y equals to beta plus x. And what do you do first? Your first step is to guess. You guess a value. Instead of trying to use the centroid method, you can guess a value for beta. Then you would calculate y hat, which is your prediction, right? And then you would say your error is y, which is what it should be, minus y hat. And your goal would be the error is y minus y hat squared. So your goal would be to minimize the squared error, minimize the squared error. So this is why we call it the least squared method, because your goal is to minimize the squared error. You just start by guessing the value for beta, and you keep updating this beta until the error disappears. And a machine learning model can do this, right? You can initialize beta to anything, and you can initialize beta to what? If you're smart, what can you initialize beta to? No one. You can initialize beta to the slope calculated from the centroid method. And then, which gives you a really good starting point, because then you will be starting, not from the beginning, you'll be starting from a really good model. And then you would calculate the error that this model is generating, and you would try to minimize that error. And then after a threshold or after a tolerance level, you would stop. So this way, this is what will happen. And this is, in fact, so you would start at this point, and then you would see that your machine learning model begins to push this line up, 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 until, it's just a little bit better. So, and because we randomly generate the x, right? Because we randomly generate the x's and the y, you see this picture is just a little bit different this time. But this model is suffering in the exact same way. The slope needs to reduce a little bit, right? So this needs to go down a little bit, and this model will be perfect. And the least squared method can easily adjust this line and put it here, because it tries to minimize the error, right? It's not using the centroid is a good starting point, but then least squared will try to minimize the error, and then kind of it will know that it should objectively minimize this, right? And in fact, what I would like for you to do is, not only do I want you to do the least square, but I want you to print out the result at every point, and then you hold the plot so that we can kind of see how that slope kind of adjusts and moves until it gets to its final resting point, and then you can stop based on a max iteration or an error tolerance that you find acceptable. Okay, good. But okay, so like I said before, the centroid works on the principle that we're regressing the mean, and you can calculate the slope of the line as simply the relationship between the mean of the input and the mean of the output. That's the centroid method. Least squared method, you can initialize the coefficient to any value, and then you would calculate your error as whatever you predict from this value and what it should be. So y is what it should be. Y hat is what you predicted from your guesswork or your chosen value of beta. Then you square it. That will give you the squared error. And then the sum squared error would be you sum it over all of the realizations of y, meaning that all of your data and the data points. And your objective is to minimize the squared error. So you would have to you can increase the value of beta, see if the error goes down, then you can keep increasing the value of beta. If the error goes up, then you know you need to reduce the value of beta until the error goes down. You keep doing this until the error goes up again, then you've reached you've reached what we would call an extremum point or a minimum. So for those of you who don't understand, since it's a squared error, it will be a quadratic function, and a quadratic function is like this: it's u, and you're looking for the value of beta at the minimum, right? Value of beta at the minimum of this squared error, this y minus y hat squared, and if you sum this over all the realizations, yi and y hat of I. And so your goal is to find the value of beta, because don't forget that y hat is a function of beta. So let me just put it here so that you want to find the beta for which this value would be the smallest. So if you're reducing beta, if for just a line in a two-dimensional plane, you will keep reducing it in using a step length until all of a sudden the error goes up again. So you'll be going down, you will get here, and then you will see that your error begins to go up again. So you know that you need to stop somewhere around here. And this would be the value of beta that minimizes that quadratic error function. And that's the value of beta that you're going to use to plot your line. And what I would like for you to do, of course, is if you in fact take my advice and you initialize beta to the centroid function, then as you begin to adjust the value of beta, you should be in some sense plotting this graph, and it shows how the slope kind of changes, and that slope fits the data some more. So this would be on the homework. All right, any questions? Any questions? Dong, since you're the most dominant student in this class, can you summarize for us what I've said the homework is going to be? I want to make sure that you understand it.
The homework will be regarding the code in Python, and we need
Yes.
to define the least square functions.
Yes. And what's the least squared function? How does that work? What will you be doing in there?
The least square functions, we will find the functions. We will compare the predicted and the exacted values, and we will try to minimize it.
Minimize the error, because
Yeah.
when you compare the predicted and the exact, you subtract them, right? So the difference would be the error. So imagine that the exact value is 5, the number 5, and you predict 3. What is the error? The error is 2. So it will be a square of the error. So 2 squared, that's 4. And then you would sum it over all your data points. So your goal is to minimize that error. So in high school, right? In high school, I'm sure they told you a quadratic function. A quadratic function is a function or a polynomial that has the power of 2, something like this. When you plot it, it looks like a U. This is, so you're trying to find the beta such that that error function will be at its minimum, right? So this is what you're doing graphically. So essentially, you will keep changing beta until that squared error goes down, right? So the squared error keeps going down, and then you keep changing beta until so you're going down this path. It's called a descent algorithm. You keep descending and descending and descending by changing the value of beta. You can simply be reducing it, right? Imagine you started with the coefficient in one dimension, right, is 3, and then you change it to 2.9, and then 2.8 and 2.7, and the error keeps going down. You keep changing, you keep reducing it until the error goes up. Imagine you go to 1.9, and all of a sudden the error goes up. Then you know that somewhere around 2 and 2.1 is your correct beta, and that's what you would return, and that's what you're going to use. So you need to be able to stop correctly at the minimum, and then when you plot your new line, right? When you plot your new line, instead of using model coefficient, which we have calculated from centroid, we're going to be using the model coefficient, which we've calculated from the least squares method. Regardless, they are both calculating the model coefficient. Only in this case, we're using the centroid one. When you implement least squares, this is also going to return coefficient, which we're going to use to plot our line. And in fact, we can compare the line from centroid with the line from least squares. Does this make sense, Dunk?
Yes.
Excellent. Thank you. Okay. Okay, so before we go, I would quickly now extend this idea to logistic regression. And then Jessica is going to tell us what this entire class was about. So because I called Dong, so it's fair that I call someone else. And so I'm telling you ahead of time, it's going to be you. So get ready to tell us what we learned today. All right, so now we have a good amount of experience with the data set that has a decent linear relationship. And we know we can feed a line through it, and it's nothing special, it's just a line. It's the equation of a line. When we use the centroid method, we simply calculate the slope by regressing the means of the distribution. And even when we use the least squares method, we're still regressing the mean, only that this time around, instead of just using the mean, we can minimize a quadratic error surface, right, which is the sum squared error. And this usually provides a better fit than the centroid approach. So still using the same idea of the equation of the line, we could say that we can have some form of a transfer function, an S-step function, such that when a threshold has been crossed, we would say that the group is 1, and when it's below a threshold, we say the group is 0. And you can kind of think of that threshold as this red line. So again, we're using the line again in a different way this time. The way we've used it before is to put it through the data set. But now we're saying if you cross the line to one side, you are a square, and if you cross the line to another side, you are a circle. And the way it works is essentially by using this thing called a logistic function. So the logistic function is 1 over 1 plus c of t, and t is, of course, what you have here. So f of t is your y-axis, and t is your x-axis, right? So when you have a t to be minus 6, you have your f of t, which is your y, to be 0, and then you can see that this function saturates at 6, and then it stays there. So the f of t can only take a maximum value of of 1 and a minimum value of 0, and it saturates at 1, right? So t is the x-axis and f of t is the y-axis. This is, of course, not strange because y is equal to f of x. So since t is equal to x, so of course, f of x or f of t is our y. So this makes sense, and this is the point of the logistic function. But how do we use it? Well, here we go. So instead of, we already know that t is related to our x, and our x is our data set, and our w is our coefficient. So this is everything we know about the linear model, only that now we are putting it in the logistic function, right? We are saying that, let's go to our notes. And so what do we know, right? We know that y equals to beta x, right? We know this already. And we know we can calculate this from the centroid method. We already learned this now. So to be able to use this for classification, we take this and we stuff it into a logistic function, which is an S-shaped function. All right. I didn't draw that well. And still, it's not well drawn. And this is better. Then I would draw this like this. Okay. So, man, this is the worst picture ever. But this is the x-axis, this is the y-axis, and this is 0. So, of course, y is equal to 0 after a certain point, and y at this point is 1 after a certain point of x. So the point of this is that we can use this function easily for classification. We can say that you belong to a class once the value is greater than a threshold. In this case, our threshold could be y equals 0.5. We could say our rule could be class 1 if y is greater than 0.5, greater than or equal to 0.5, and we can say class 2 otherwise, meaning, y is less than 0.5. Simple. So to use the linear regression idea for classification, all we have to do is to take this and stuff it into the logistic function. And we know that the logistic function is f of t equals to 1 over 1 plus e to the minus t. This is the standard logistic function. And if we can just replace this t with our beta x, which is our y, in linear regression, then we can use the logistic function as a binary classifier. So that's what this is about. So it is not rocket science, and it is not magic at all. And so we take this logistic function, we replace the t with our beta x, which is the coefficient of x, and the coefficient of x is in fact our model, and that is it. And we say that this is the probability of a class given x. Given that we've seen x, the probability that of a positive class is this, and then we have the same thing for the negative. The probability of the negative class is this, right? So this one will give us the probability of positive class. This expression gives us the probability of negative class. And if this probability is greater than this probability, we choose positive. So that's the next step, right? Forget about this expression. We really don't need it. So we're saying that, imagine that we have used the least squares method to calculate the value of our coefficients, which you can very much do first. Then from there, we can calculate the probability of x belonging to the class of positive. And then we can calculate the probability of x belonging to the class of negative. And we can choose the class that maximizes the probability. That's it. So whenever P of C plus is greater than P of C minus, we predict C plus or the positive class. Otherwise, we predict C minus. Okay, otherwise we'll predict C minus. So let's look at how a logistic regression model would work on our data set from last time. Okay, and then we can also see the decision boundary as well. So this is a logistic regression model, and I will give you this code. And really, this code is very similar to my code from last time. In fact, there is only one change. So here I decided I changed this to from instead of sklearn.svc, I'm from sklearn.linear model. I import logistic regression. This is the only difference. Instead of bringing in support vector machine, I brought in logistic regression because it's already been done, and I just ran my code as is. And now you would see that we have what happened. We have the same plot as we had last time. All right, I think I'm back. Can you hear me? No one can you hear me now?
Yes.
All
I
right.
can hear
Okay.
you.
So this is the same problem that we had last time. You can see the decision boundary is the same, and also you can see the mixture between the height and weight. They're completely mixed together. It's hard to be able to separate this in 2 dimensions, which of course, now when we go to 3 dimension, you can see the decision boundaries that we generated to be able to separate the sample. And in fact, you can kind of see the separation yourself, if you will. Okay. So the linear regression definitely works well. In fact, let's show. I want to show the actual decision boundaries, but it's going to be tough to see in 3D, but I will kind of give you a hint of where it is. And then we can okay, so these 2D slices. Okay, so if you look at this black lines, it's kind of doesn't go well, but it's like a shadow of the real decision boundaries, and this is what the model learned. So you can it allows you to kind of be able to compare, if you will, the SVM model and the SVM model and the logistic regression model to see the decision boundary that they both construct, or you can just visually inspect it with this 3-dimensional plot. Anyway. Okay, so this is where we're going to stop today, and you can see that the logistic regression model also has an accuracy of 1 and has the same model characteristics as the SVM model because this is quite a simple problem. But it's nice to see the decision boundaries that they both construct and whether or not they're slightly different. Whether SVM, of course, still has a dominant, constructs a much more dominant decision boundary, and I think that in fact it does. All right, so in the so you already know that you would do the least square thing, and you would also have to extend it to logistic regression by using this formula, and then you compare it to my own logistic regression code, which actually is not written by hand. Right, so yours would use this formula, and mine, which I would give you, uses some sklearn, right? So, and then you want to see if there is a difference in your own model and what you can import from sklearn in terms of performance. All right, okay. So anyway, I would describe all of this, and as usual, you're going to do the work, and you're going to record a video of yourself presenting it, talking about it, and maybe you don't know why I'm doing this. We're out of time, so Jessica, you escaped, but next week you would give us the recap. The reason why I ask you to record a video is because when you keep talking about this and you keep recording your video, you're also kind of getting ready for your seniors and you're going to graduate next year. It also prepares you for being able to talk intelligently about these models. Someone asks you about these models at a job interview. You've already done a presentation in the past. Your brain can pull from something, but if you've never done it, your brain cannot pull from anything. So yeah, when you get the high-paying job, then you're going to think about the fact that I made you do this, and then you'll be happy. Okay. Thank you guys for coming, and I will see you next week. Bye-bye.